Hi, welcome. So I want to introduce this next worksheet. This is the worksheet on chemical reactions, and I want to put it in context of our textbook, which sections we're covering, and how it fits in with the other materials we've worked on. So I am making this video to use with the Timberlake textbook, and specifically to cover electrolyte solutions, which I've added to match this textbook. And what I like to do is bring in uh, all of the different types of chemical reactions into one section. So we are working from multiple chapters. In chapter 7, we introduce the chemical reaction and balancing, and then the Timberlake book goes into stoichiometry and mathematical calculations, and then later into energy. So we've actually covered some of the sections in chapter 7 already. But then we're going to jump from the chemical reactions balancing section right into chapter 9 for solutions, looking at reactions in aqueous solutions, water-based reactions, and that aligns perfectly with our lab for this week, where we're going to view a couple different kinds of reactions. The section 11.7 is just the reactions for acid-base chemistry, and I can see I left some sections off here because I was thinking, where are we going to cover the acids? So we'll come back to that and look at, I like the way this book covers acids in full in one chapter, but we're going to introduce some of the types of reactions that are acid-base reactions as we classify what kind of reactions. Acid-base reactions are often a double replacement type of reaction that forms water as our new substance. And so I like to have that in the context of all of the chemical reactions, and that is why I've pulled these sections together. If we have an electrolyte solution, that means that it conducts electricity. The electrons we put in can move through the solution, and we see that with this experimental setup here, where there's these two electrodes, it's plugged in. If the electrodes can conduct electrons between them, then the light bulb will turn on. If there are no ions in solution, so even pure water does not conduct electricity, the light bulb does not light up. There's no way for the electrons to get through that solution. Now we might have a weak electrolyte. A weak electrolyte allows some electrons to flow between those electrodes, but the light bulb only lights up a little. It's dimly lit. It's not a free flow of electrons the way it is with a strong electrolyte. So electrolyte means there are ions in solution. And weak and strong are now technical terms. Write down strong and weak are technical terms, so we're going to be using them in a very specific way. So let's take a look at what it means for that solution. If it's a strong electrolyte, super bright bulb, that's something like sodium chloride. That is an aqueous ionic solution. So every single sodium chloride, every formula unit of sodium chloride breaks apart into ions, and those ions move freely in the solution. So if there's electrons coming in, that's going to influence the motion of those charged particles and allow that charge to be conveyed through the solution. And that's why the electrons can flow. And then the light bulb lights up. Now if you have a weak electrolyte, this is something that stays intact as a molecule. Maybe if I try stop share and reshare, I'm going to edit this out, maybe, hopefully. Share this again. Try to annotate. Okay, let's see if it works. So acetic acid, yes, okay, it's working. Acetic acid is, excuse me, is a weak electrolyte. Most of it stays together as a neutral molecule, but a small amount will break into those ions, the acetate ion and the H+, because it's an acid. Acids will form that H+ in water. So even if it's weak and not very much breaks apart, any little bit of ionic character will allow the electrons to flow. Now, if we look at something that's a non-electrolyte, this could be a little confusing. These are molecules. These are nonmetals with nonmetals. Things like sugar is another example, and let me write that down here. Sugar is something like, it's like C11H12O11. It's got all of these OH groups, but they're not acidic. And similarly with this ethanol, that OH, it's not acidic at all. That hydrogen stays together with oxygen. So these are molecules, and they don't allow electrons to flow. There's no charged particles forming, even though they dissolve. So whether charged particles form or not, we can measure very directly, and it's super important information. So we're going to go through classifying and getting to know, right? A lot of this is just getting familiar with a bunch of different substances. So we're going to go through and identify what our strong and weak means and which ones will conduct electricity. So now I am jumping into 11.3, just a section of it. And let me write that down because I missed that in my listing. 11.3 is strong and weak. Okay. All right, so if it's an acid, that means that when you put it in water, it's going to give those H+. The H pluses are going to come apart to form H+, and then whatever that other bit was, that other part of the acid is the negative charged. Strong acids dissociate completely. Like every single one of those molecules breaks into charged particles like sodium chloride. Every single one of those breaks into its ions. So we can call that the degree of ionization. If it's all ions, then it's strong. Now, if it's weak, that means only a small proportion break into ions. And so I'm introducing this in the acid-base sense, and then we'll wrap it together with the ionic compounds that we've looked at. All right. The other thing about acids is that they are related to water. And so when we write something like H plus aqueous, aqueous means that it's in water, it's surrounded by water. But if we're balancing, we might also show it as the hydronium ion, where we're showing that water that it's connected to explicitly. So these are kind of interchangeable. The only time they really make a difference is when you're balancing your equation. Did we include the water molecule or did we not include the water molecule in the balancing? But conceptually, those hydrogens are always associating with the water. So let's take a look at a strong electrolyte. In this case, our example is HCl. So hydrochloric acid. Oh, and let me clear those boxes. Every single HCl, so we have HCl, and all acids are aqueous. But what that really means is H plus aqueous, and I should maybe make that super, I'm just going to write it. H plus plus Cl minus aqueous. So anytime we see HCl aqueous, we'll keep it together so it looks like a molecule even though it's not a molecule. But we know because it's strong, it's actually completely independently functioning. Those H pluses would rather stick with the water as a hydronium ion than stick with the chlorine. So what we see are the chlorine atoms, ions. The chlorine ions are green, and they're surrounded by water with that ion dipole interaction. And then we have our H3O plus hydronium ion, and it is also surrounded by waters that stabilize that charge. And every single one of those is ionic. That light bulb lights up bright. Now, if we look at a weak acid like acetic acid, this is the main ingredient in vinegar. So you're probably familiar with it. You've probably eaten it. Most of these stay together as neutral molecules. So there's one, there's one, there's one, There's one, there's one. They're in there, they're just not breaking apart into ions. They're staying together as a neutral molecule. But one of them splits up. And so that is enough to allow the electrons to flow. And that's what it means to be weak. Weakly lit light bulb. Weakly conductive. So in terms of our chemical equations, HCl, we just need to know, we're going to memorize that is a strong acid, HCl, but it always goes one-way arrow, completely dissociates. So what it means to be strong means 100% dissociation into ions. True for nitric acid as well. The H plus and the NO3 minus completely break apart. The NO3 minus, those are the polyatomic ions, right? So that stays together as an ion. Now, if it's a weak acid, that means that everything is in there at once. So a weak acid means only a small amount dissociates. I spelled that wrong. There we go. Just a small amount. And it's usually for these ones, both of these have the same relative values. For every one that breaks apart, one H plus, one F minus, there would be 10,000 that stay together as neutral molecules. So that's what I mean by only a small amount will break apart. Mostly it's the neutral molecules. And that again is acetic acid with H plus and acetate ion. The two-way arrow means that if more of these form into ions, they come back together and reform that reactant again. So they reform the neutral molecule. There's a balance. All of these things are in solution at the same time. It's just balanced more towards the reactant side, but we still are going to write those products because they affect the behavior. Why would they affect the behavior if it's only 1 in 10,000? Well, think about a mole of particles in there. If we have a mole of acetic acid in our volume, there's going to be a lot of acetate ions and H plus ions, right? 10 to the 23rd. There's going to be a lot of them, even if they're heavily weighted towards the neutral molecules. All right, so strong and weak does not mean dangerous. It means what kind of arrow is it, right? If it's strong, that gets a one-way arrow. If it's weak, it gets a two-way arrow and everything's in there at once. Okay. So let's talk about the electrolytes. So this is anything, not necessarily an acid. So we're back out of chapter 9, back into, oh no, it is chapter 9, isn't it? Sorry, I'm not 100% sure on all the details. Okay, so strong electrolytes conduct really well. They tend to produce many ions in water, and we'll get that one-way arrow. And of those strong electrolytes, we can have strong acids, strong bases, and all soluble ionic compounds. So as we go through and we identify whether our products are solid or aqueous, if it's aqueous, that means it's going to be a strong electrolyte. And then the strong acids and bases, you just have to memorize. So I try to give you a lot of scaffolding to try and remember that. And here on the periodic table. So when we're talking about ions, notice those polyatomic ions, nitrate, perchlorate, and sulfate. When we fill them up with hydrogens, those are the strong acids. Plus the HCl, HBr, and HI. Now HF, remember fluorine is so special. It's a weak acid. I don't quite really know why. Like, I have explanations, well, how we justify it, but it just seems so strange. But HCl is in our stomach contents, and then HBr and HI are also strong, which means they can break completely into ions. But fluorine is so electronegative that it keeps that hydrogen around. I don't quite get it, but that's okay. Just these are your 6 strong acids that break into ions completely, and they're acids because one of those ions is the H+. Now, strong bases, when we look at our reactions, we're going to be building an H plus with an OH to build a water molecule. So the bases, the strong bases, give us those OHs, right? We see all those OHs on there. And those also have a relationship to the periodic table. They are the little Tetris shape here. Lithium, sodium, potassium, and then scooting over one to calcium, strontium, barium. So those are the strong base cations. When those metals react with water, they form strong bases that dissolve. We will also see this behavior reflected in the solubility rules while we're working with them. Okay, so if it's on your list, it's strong. If it's not on your list, it's just a weak acid or ionic compound. Okay, let's move on to weak electrolytes. So these are things that conduct, but not well. So there's a little bit of ionic compounds in there, but not enough to just completely carry all of the electrons. So our solid ionic compounds will be weak electrolytes. So they dissolve a little bit. There's a tiny amount, but again, times 10 to the 23rd particles, there's enough that some of the electrons can flow. So if you're categorizing your ionic compounds as solid or aqueous, solids will be weak electrolytes. There's just a tiny bit dissolves, it's enough. If it is an acid, you recognize that it's an acid, but it's not on your list of strong acids, then it's going to be a weak acid. And these are going to get the two-way arrow. Everything is present at once, and we will work with that more when we talk about the acid-base chapter later in the quarter. Okay, so weak electrolytes are the weak acids, weak bases. We'll learn to recognize those. And then insoluble ionic compounds. Those are the ones from our solubility rules that we're going to label as solid. Okay, and then possibly the trickiest part of this are the non-electrolytes. These are molecules. They may dissolve, but when they dissolve, they don't break into ions. So these are things, when we talk about solubility, you may have heard the phrase like dissolves like. And what we mean are similar intermolecular forces. Right? So if it's something that is polar, it will dissolve in polar solvents. If it's got hydrogen bonding, it's going to be great with other solvents that have hydrogen bonding. If it's nonpolar, it's going to dissolve best in something that's nonpolar. So when we talk about sugar and alcohols, this one can be a little confusing because it looks like, we often have that visual question like, wait, is this a hydrogen that comes off like an acid? Well, notice in our acids, a lot of times we'll write those acids, the H that comes off at the beginning. Here's an H at the beginning. And then again, even with this acetic acid, the fact that that H is at the beginning is indicating that it comes off as an acid, whereas these H's are on carbon. Carbon doesn't let its hydrogens go. It's going to hold them tight. All right, so back down to, oh no, we were here. Non-electrolytes, sorry. Non-electrolytes, sugars and alcohols are the typical ones. Hydrocarbons also, well, they don't really dissolve in water, and they definitely don't really conduct electricity. So these are non-electrolytes, and the light bulb just doesn't even light up. Okay, so when we're talking about ionic compounds, we want to be able to visualize the main things that are in there. And so if we take sodium chloride, and again, this is kind of assuming we did the ionic compounds, solubility rules. Sodium chloride, when we look at our list, we'll find sodium in rule number 1 is always soluble. So when it's put with water, it's going to go directly to ions, all the way to ions. Now we may write it in our equation as NaCl aqueous because of we'll need to write neutral compounds. But in our minds, when we visualize, they're completely separated in ions because they dissolve in water. Sodium phosphate, so that produces 2 ions. Sodium phosphate has that formula NH4 3. It's got 3 ammonium ions for every 1 phosphate. So that gives us 3 of those and 1 phosphate, total of 4 ions. So that's going to conduct even more easily. So let's classify, and this is kind of a difficult skill. This is one of the challenging parts. So try to work through it and get through what you can. And I'm going to draw these pictures in the beakers down below as well. Okay, so we want to identify, is it an acid, is it an ionic compound, or is it neither? And then we want to say, is it strong, weak, or non-electrolyte? So you'll need your list of strong acids and bases, you'll need your solubility rules, and you'll need that's it. Okay. HCl. This is an acid and it is strong. And I'll go ahead and draw that down here just to get us going on it. So when I use these beakers, and again, this is a great way to work through it. I'm going to draw my water line up here. This is a strong acid. That means it's going to form H+, and maybe I'll go ahead and keep those superscripted. And it's going to form a Cl-. Every single one of those HCl molecules breaks apart. So that's it. That's the main things we have in solution. Now let's take a look at magnesium hydroxide. If we look on our solubility rules, we go all the way through to the last rule on the right side, rule number 10, says hydroxide ion, so we expect it to be solid. But calcium, strontium, and barium make it aqueous. Those are the strong bases. Magnesium is not a strong base anion. So this is going to be a solid. It's going to be weak. Oh, let me write ionic compound that is weak. Okay, so how do we draw that in the solution down below? These are going to stay together. So magnesium OH2, and that's going to stay solid. Now, there's a tiny bit, it's a weak electrolyte, there's a tiny bit of Mg2+, and then the OH-, a couple of those. So even though only a few of these compounds dissociate, When they do that, it's going to be 1 magnesium and 2 hydroxides to keep that neutralization, that electrically neutral solution. So the main species is the solid with just a tiny bit of ions that form. Okay, next up, oh, this one's a little tricky. What is this? If you look at your solubility rules, and I think I talk about this in the other videos, we might get all the way through to rule number 5, carbonate, and say, oh, that's solid. But it's not solid. Why not? First, it starts with an H. This is carbonic acid. This is an acid. And all acids are aqueous. So this is an acid, and it is weak because it's not on our list. Okay, so how do we draw that? Here's our water level. Okay, it's weak, which means that most of it stays together as a neutral compound, H2CO3, dissolved as a neutral compound. But it also can form H plus and HCO3 1 minus. So I'm just going to pull off that 1 hydrogen. We could show 2, but it's weak. So it's not going to form a lot of ions, just a little bit of ions. The predominant species in solution is the neutral compound. So it is a weak electrolyte. All right, next up, strontium hydroxide. So we see a metal with a nonmetal, so we do look on the solubility rules, right? With the carbonic acid, we wouldn't be looking because that's nonmetals with nonmetals. Okay, so we get to hydroxides. We get all the way to that last rule, and then strontium hydroxide is soluble. So that means that it's a base. It's a strong base. We could classify it as a ionic compound. And it is strong. Strong electrolyte. Okay, so how is that going to change what we draw in the beakers? We're going to have that strontium dissociated into the 2+ ion. And then we're going to have those OH minuses. Twice as many hydroxides running around. None of it stay together as a neutral molecule. So that's what it means to be strong. That neutral molecule, that reactant side is gone. Completely ionized. Okay. Now, to make room for stuff, I'm going to go ahead and erase all of this stuff. And then we'll use those bottom beakers next. Okay, aluminum nitrate. Aluminum nitrate. Which rule do you get to? I have rule number 2, nitrate. All nitrates are soluble. They make everything soluble. Okay. So this is an ionic compound. It is aqueous. Oh yeah, sometimes I ask students to fill in the solid aqueous business over here. Remembering that all acids are aqueous. There we go. And we just said this is soluble, aqueous, so that means it's a strong conductor, strong electrolyte. So let's go draw that. Aluminum nitrate. Here we're going to have aluminum carries a 3+ charge. And then I'm going to have NO3 1-. I'm putting the charges in parentheses. And we're going to have 3 of those. Actually, let me just put a 3 in front. So there I'm using that coefficient. So 3 of those. That has 4 ions total. So it's going to conduct really well. All right, let me scroll these guys up. And we are at C2H5OH. What is that? Do you recognize that at all? Oh darn, I didn't get everything. That is ethanol. That's ethanol, good old vodka. Okay. This is what was I choosing from up here? Acidic or it's none of those. It's not. It's not. This is a molecule. This is yeah, I'll just write molecule. This is a non-electrolyte. So that's just going to stay together in solution. It does dissolve, but it doesn't break into ions when it dissolves. How about HNO3? Is that on your list? It's got an H at the beginning, so it's an acid. It is on your list. So this one is an acid, and it is strong. So there are no neutral molecules remaining. And then here is ammonium phosphate. Looking at the solubility rules, rule number 1, we meet ammonium, so it is aqueous. Aqueous. And so is this one. All acids are aqueous. This is an ionic compound, and this will be a strong electrolyte because it is aqueous. Okay, so let me scroll down and fill in our beakers down here. Okay, this one is just going to be C2H5OH Stays together as a neutral molecule. It engages in hydrogen bonding with the other water molecules, dissolves completely, but no charged particles. Unlike nitric acid, it's going to form completely H plus and NO3 minus. And then ammonium phosphate, we're going to have the NH4 plus, and there's going to be 3 of those, plus our PO4 3 minus ion, strong electrolyte. Okay, then we're going to move forward with our net ionic equations. Now this section on electrolytes I insert right in between our double replacement reactions and our net ionic equations introduction. And it's going to help. It's going to help write those net ionic equations because we need to show whether they break into ions or not, or whether they stay together as a molecule. Okay, so that's how it fits in. Let me know how you're doing. If you have any questions, hopefully this helps to smooth out the path as we move through this content remotely. All right, have a great day.